Okay, student, then we'll see here, then you do this integration part or not. Now, this is the unit ramp response in time domain directly without doing this, okay. Now, which is nothing but integration 0 to t dt minus integration 0 to t e power minus t by tau dt. If you do this integration directly, you can get the answer. Unit ramp response in time domain, unit ramp response in time domain, which is equal to integration dt is t, upper limit is t, lower limit is 0. So this is e power minus plus tau and e power minus t by tau over the limits 0 to t over the limits 0 to t. Therefore, finally, this is t minus tau into e power minus t by tau. Upper limit is e power t, lower limit is e power 0. Therefore, e power minus tau plus tau into e power minus t by tau. Now, this is the students unit ramp response in time domain directly. You can get the answer or not. Otherwise, this is the direct method. Otherwise, if you don't have this particular relations, conversion of one response to another response, then what do you have to do? You have to find a by s, b by s square, c by 1 plus tau s, a by b by c by 1 plus tau s, find a, b, c values, and again you apply the inverse Laplace transformation. It will take a more time. Okay, this is the easy method, and you have a relations from one response conversion to another response conversion. And one more thing also, then this is the response. This is the unit ramp response. This is not used practically, only for theoretical or mathematical calculations, because this input is nothing but a bounded input or not. It is moving towards the infinity side. This is a unbounded input. Now, for unbounded input, then we are not used that unbounded responses as unit ramp responses or unit step response or any kind of responses, which we are not used. Okay, that's what only the practical response is nothing but step response. Theoretical response, we can directly go for the impulse one. Okay, that is the best one for theoretical, and the best one for practical is a step response. Okay, this is for calculations part. Okay, you just take this one. I hope you finish this one. Just do that integration part. Okay. Right. Now, students, now we'll see case 4. Now, this is case 4. Now, the reference input is unit parabolic input. Now, this is unit parabolic input. This is also an unbounded input, which is not used, only for theoretical calculations. Okay. Now, R of S is Laplace transformation of 1 by 2 into t square, which is equal to 1 by s cube. Now, previously you do the correction, Laplace transformation not u of t, Laplace transformation of t into u of t. Therefore, that is 1 by s square. Okay. Now, this is R of S, which is equal to 1 by s cube. Again, the same procedure, a by s, b by c by and d by ABC calculations. This is a lengthy analysis. Okay, you don't do that one. Then this is the easy analysis. This is the unit step response, and you can get the unit ramp response. Now you have a unit ramp response. Then you can find directly unit parabolic response. What is the relation between unit parabolic response and unit ramp response? The unit parabolic response in time domain directly, the unit parabolic response in time domain directly, which is integration of unit ramp response. Integrate the unit ramp response. Integration of t is nothing but t square by 2 or not. So which is nothing but integration 0 to t. Now this is the unit ramp response, which is t minus tau plus tau into e power minus t by tau into dt. Therefore, which is nothing but integration t dt is nothing but t square by 2 minus tau into t. Now minus tau square plus tau square minus tau square into e power minus t by tau. This is a unit parabolic response. Okay. Now this is the unit parabolic response now from the unit ramp response, and this is the unit ramp response from the unit step response. Now these are the relations for converting from one response to another response. Okay, this is the relations for converting from one response to another response, such that you can easily find the responses. You have another response is known to you. Okay, so this is the relations which we already have in the basic portion. The same thing will be utilized and will continue. But this unit ramp response and this unit parabolic response, which is not used practically, because these are the responses for an unbounded inputs, and it produces the unbounded response, which is not useful for practical analysis. Okay, note on this, and we will see the another case also. Okay. Now the students, now we just see the unit impulse response, unit step response, unit parabolic response, unit ramp response. Okay, for the first order system, same first order system only. Okay, now in the continuation of that we will see ramp input, parabolic input, step input, impulse input. Now we'll see the case 5, sinusoidal input. What I am giving? Now I am giving for a sinusoidal input. What happens if a sinusoidal input is given? Now the sinusoidal input. Now students, whenever the sinusoidal input is given to a system, if you give the ramp input, ramp response, step input, step response, parabolic input, parabolic response, impulse input, impulse response. Now similarly sinusoidal input, what you will get? Sinusoidal response. If you give a sinusoidal input, then definitely we are expecting the sinusoidal response. But what should be the changes you may observe here? Now, our control system, which is a combination of RLC circuit, therefore you know that this is called as a linear time invariant system, right? Now this is a linear time invariant system. For a linear time invariant system, see the students here, for a linear time invariant system, this is the input and this is the output. For that linear time invariant system, for that particular control system, what I am giving is, for that particular linear time invariant systems, now I am giving input R of t as a sinusoidal input. Let us assume magnitude is A, frequency is omega, and phase is some theta. Now for a linear time invariant system, if input is sinusoidal, student, output is also sinusoidal. Output is also sinusoidal. Now the output is same A sine omega t plus theta. So then where is the changes? If input is sinusoidal, output is also sinusoidal, only the difference in magnitude and the difference in phase. This magnitude is going to be changed, and this phase angle theta is also going to be changed. So if the input is sinusoidal, output is also sinusoidal, only the difference in magnitude and only the difference in phase angles. Okay, now I can easily find what should be the change in magnitude at output side, what should be the change in phase at output side. If you measure those two changes, then the sinusoidal input and sinusoidal response both are same, only the difference in that particular change in magnitude and change in phase angle. Is it right or not? Yes. So, but if you have one common point here, what is the frequency of oscillations at the input side? Omega radians per second. What is the frequency of oscillations at the output side? Omega radians per second. This is the key parameter to find these two changes. So at the same frequency of oscillation, what should be the change in magnitude? What should be the change in phase? We need to be identified. We need to be calculated. Now the students, I am asking one question, one small like basics. Now this is A plus IB. This is the real part. This is the imaginary part. Then what is the magnitude? The magnitude is nothing but square root of real part square plus imaginary part square, and a phase angle is nothing but numerator is positive tan inverse imaginary part by real part. Therefore B by A. You know that. Okay. So you know when angles are multiplication theta 1 into theta 2, then the overall angle is nothing but addition. And similarly, when angles are division theta 1 divided by theta 2, which is nothing but the overall angle is subtraction theta 1 minus theta 2. That is the reason why whenever there is in the denominator, you can take an angle of minus. Okay. So let us take one small example. 1 by A plus IB. Therefore, 1 divided by magnitude is square root of A square plus B square. Now positive constant angle is always 0. Tan inverse imaginary part is 0. 0 by 1 means tan inverse 0. The numerator is 0 degrees. Denominator is tan inverse B by A. Theta 1 divided by theta 2. Therefore overall angle is theta 1 minus theta 2. Therefore 0 degrees minus tan inverse B by A. Therefore minus tan inverse B by A. There is a imaginary part, real part. Then these are the few basic formulas which are helpful here, because here we want to find change in magnitude and here we want to find change in phase angle, that is plus or minus denominator numerator, it will be different. Okay, take a small basic formulas, you already know that, I just recollect that one. Okay, then we can easily find what should be the change in magnitude and what should be the change in phase. Take that one. Okay. Now with one problem you can understand this, how to get the sinusoidal response. Okay. Now you have a handbook of control system. In that, now this is the chapter 2 and topic is time domain analysis of first order system. Now in that question number 1, with one problem you can understand. Okay. Now this is the question number 1 in your workbook, and in this topic is time domain analysis of second order system. In that question number 1, what is question number 1? Now the question number 1 is, now consider the system whose transfer function C of S by R of S, which is equal to 1 by S plus 1. Okay. Now what is the question in our workbook? Question number 1 in the topic, by considering the system is having a transfer function of C of S by R of S equal to 1 by S plus 1, determine the sinusoidal response. What is asking? Determine the sinusoidal response for the input. Input is given. Determine the sinusoidal response for the input R of t equal to 10 cos 2t plus 45 degrees. He is giving this. What is the question? In our workbook, question number 1, find the sinusoidal response by considering the system transfer function C of S by R of S equal to 1 by S plus 1 for the input R of t equal to 10 cos 2t plus 45 degrees. Now the students, I am asking, whenever the sinusoidal input is available and the response is sinusoidal, first you find the sinusoidal response. You first draw the sinusoidal response. Now, what is C of t? Same. Sinusoidal input response is same, C of t, which is equal to 10 cos 2t plus 45 degrees, and this phase angle is going to be changed and this magnitude of 10 is also going to be changed. Is it right or not? That's what I'm saying. Sinusoidal input, sinusoidal response, change in magnitude, change in phase. What is the key parameter to find that change in magnitude and change in phase? Is the frequency of oscillation. At the input side is 2 radians per second. At the output side is also 2 radians per second. So the frequency of oscillations at the input side and output side is 2 radians per second. So at the same 2 radians per second, now we want to finish that particular analysis. At 2 radians per second, what should be the change in magnitude and what should be the change in phase? Now, let us assume S equal to j omega, assume real part is 0. So S equal to j omega, replace S equal to j omega by assuming real part 0, because this is a pure frequency response analysis, sinusoidal input, sinusoidal response. So if you replace S equal to j omega, see the students here, C of j omega by R of j omega, which is equal to 1 divided by 1 plus j omega. 1 divided by 1 plus j omega. Therefore, C of j omega, omega is 2 radians per second, because at input side is same, at output side is also same, 2 radians per second. Now, R of j omega, omega equal to 2 radians per second, which is equal to 1 divided by 1 plus j2. Is it right or not? Now students, at 2 radians per second, then what should be the change in magnitude? At 2 radians per second, what should be the change in magnitude? 1 divided by square root of a square plus b square, real part square plus imaginary part square. Now the phase angle is denominator, therefore minus tan inverse imaginary part by real part. Now I am asking question, at 2 radians per second, output to input at 2 radians per second, then there is a change in magnitude of 1 by root 5, 4 plus 1. There is a change in phase angle of tan inverse 2. Now the students, you just concentrate or not, output at 2 radians per second, which is equal to input at 2 radians per second. Both are same. See here, output at 2 radians per second, which is equal to input at 2 radians per second. But where is the change? At input side, there is a change in magnitude of 1 by root 5. At input side, there is a change in magnitude of minus tan inverse 2. Then it should be the sinusoidal response at the output at 2 radians per second. Now easy question. Now at 2 radians per second, now the output side, how much magnitude is changing? Now the magnitude is changing by a factor of 1 by root 5, and the phase angle 45 degrees plus or minus, now this is minus tan inverse 2. After simplify this, 45 minus tan inverse 2, and this is 2 root 5, now is a magnitude. This is the sinusoidal response for the given sinusoidal input. There is a change in magnitude and there is a change in phase angle. Okay, this is the sinusoidal response for the given sinusoidal input. Now the students, this is question number 1 in our workbook, and this is the, with this question also you can understand what should be the sinusoidal response for the given sinusoidal input for a first order system only. This is for a first order system I am considering, because we are in the first order time domain analysis, therefore I can take a first order system. Okay, note down the student this one. Okay, I hope you understand. When sinusoidal input is given, the same procedure for any system. Okay, so now in the same procedure, then in the previous GATE examination 2 marks one question is given. Now that question is nothing but in our question number 2 in our workbook of time domain analysis of second order chapter 2. Now question number 2 is same. Now students, he is giving the transfer function. The transfer function which is y of s by x of s, output y of s, input x of s is given as s by s plus p. Students, see here. Now the control system whose transfer function y of s by x of s is nothing but s by s plus p has an output. Output is given. In this question, output is also given. What is the output which is given to you is y of t, which is equal to cos 2t minus pi by 3. Now output is given y of t equal to cos 2t minus pi by 3, and input is also given. Input x of t is also given t cos 2t minus pi by 2. Now this is input and this is output, and options are also given. Oh sorry, first I read the question. Okay. The control system whose transfer function y of s by x of s is this one. Y of s by x of s is this one, and for that system output is this one, input is this one, and he is asking the system parameter p is dash. The system parameter p, and see the options also. The options are 2 by root 3 is A option, B option is 4 by root 3, and C option is root 5 by 2, and D option is 10 by root 3. Very simple question, but he is given 2 marks for the previous GATE examination, students. Okay, just try to concentrate it. If you understand the basic question and how I am explaining for the sinusoidal input, then this is also very easy for you. Okay, now see here. Now here is also, what is the frequency of oscillation at 2 radians per second? What is the frequency of oscillation at 2 radians per second? Now forget about this. You find what should be the output for the given sinusoidal input. Now y of j omega by x of j omega, which is equal to 0 plus j omega by j omega plus p, where omega is 2 radians per second, omega equal to 2 radians per second. Therefore y of j omega is 2 radians per second by x of j omega is 2 radians per second, which is equal to j 2 radians per second, p plus j omega is 2 radians per second. Now see the students, now this is the output to input at 2 radians per second. Forget about all these things. You find what should be the output. Okay, so y of j 2 radians per second by x of j 2 radians per second, which is nothing but square root of a square plus b square, square root of a square plus b square, square root of a square plus b square. Phase angle is, numerator means positive, tan inverse imaginary part by real part, denominator is minus, tan inverse imaginary part by real part. Now the students, you see here y of j2 by x of j2, which is equal to, now root 4 is nothing but 2 by square root of p square plus 4, and phase angle is tan inverse infinity is 90 degrees minus tan inverse 2 by p, tan inverse 2 by p. Am I right? No. Now this is the sinusoidal response. This is the sinusoidal response now for the given sinusoidal input. Now the students, you just identify here, this is the sinusoidal response for the given sinusoidal input. Now you can find what is output, students. Now based on this, what is output? Now based on this, the output is nothing but same as that of input. Now the output is nothing but the same as that of input, which means that y of t, which is equal to the output, which is nothing but same as that of the input, which is nothing but, now this is input p, but now this is changing to p by square root of p square plus 4. Now the phase angle cos 2t minus pi by 2. Now this plus this one, 90 degrees is nothing but pi by 2 in radians minus tan inverse 2 by p. Now the students, this is the output for a sinusoidal input. This is the sinusoidal response. Now p is multiplied with 2 by square root of p square plus 4 and 2t minus pi by 2. Now that is added with 90 degrees minus tan inverse 2 by p. Now which is nothing but, now this is the actual output what we are getting. Am I not? This is the actual output what we are getting, and this is the output which is already given in the question. So you can compare with the magnitude, or you can compare with the phase angle, whatever that is your wish. You can compare with, this is the procedure we are finding, and this is the output I can get, and this is the output is given. Then this magnitudes you may equal. So 2p by square root of p square plus 4, which is equal to 1. Therefore 4p square, which is equal to p square plus 4. Therefore 3p square equal to 4, p which is equal to 2 by root 3. P which is equal to 2 by root 3. P which is equal to 2 by root 3. Then which option? Option A is correct. I just explain, just a second. This is the transfer function which is given. Input is given, output is also given. Let us assume output is not given. Okay. If input is given, what is output? Magnitude is changing some factor. Phase angle is also changing by some factor. How much is change in magnitude? We are calculating. How much is change in phase angle? We are calculating at 2 radians per second, because input and output is 2 radians per second. And I am finding this should be the output I am getting for the given input. But in the question is already given output, no? Then that output magnitude is comparing, and I can get the result. Some of the students are saying that, no sir, this is 2t, this is 2t. I can compare with the phase angle. Not an issue, you can find. You can compare with the phase angle also, you can get the same answer, not an issue. Okay. This is a 2 marks question in the previous GATE examination. Note down the students. Okay, then I think you understand this one. Then we'll go for question number 3. Okay. before you solve question number 3, you just recollect what you studied in the time domain analysis of first order system, practical and theoretical responses. No, just recollect that, such that these remaining questions are very easy. Okay. Before we start the question number 3, just recollect what we are doing. Now this is the response of the first order system. What we are studied, practical response. Now if you see here, this is the first order system practical response. No sir, we are not doing that, we are doing this one. Both will be same if you observe clearly. What is the difference? The difference is, this is the standard first order step response because magnitude is constant. This is the standard first order unit step response because magnitude is constant and exactly equal to 1. This is the first order step response, and this is the first order unit step response, because you know that the steady state gain or steady state level or reference level which is equal to 1 for unit step. Is it right or not? The steady state level or steady state gain or steady state value which is equal to 1 for unit step. But if you observe or not, the standard first order system transfer function is actually C of S by R of S, which is equal to, you are writing 1 by 1 plus tau S, but now actually that is K by 1 plus tau S, because tau is system time constant, K is system gain. That is the actual first order system, because the control system is depends upon the system parameters, where K is system gain, where tau is time constant. Okay. Now in that case, this is the first order step response. If K equal to 1, this is the first order unit step response. Okay. Now this is the thing which is easy for you to solve the question number 3 in your workbook. In our workbook question number 3. In our workbook question number 3, what is question number 3? A first order system is initially at rest position. We are saying that a first order system is initially at rest position. See here. A first order system is initially at rest position. And one more thing also I want to say. In the question he is not mentioning step response, unit step response. He mentioning sometimes first order, second order, or sometimes also mentioning, but he is not given first step response, unit step response. While looking the question itself, you have to identify that is comes under first order step response or unit step response. Okay. How you can identify? If the reference level is 1, unit step. The reference level is some constant level, step response. Now what in this question, question number 3 is, a first order system is initially at rest position and the response reaches 1.1 volt. The response reaches 1.1 volt after 4 seconds. The response reaches 1.1 volt after 4 seconds and finally reaches a steady state value of, a steady state value of 2 volts. And finally reaches a steady state value of 2 volts. Finally reaches a steady state value of 2 volts. The response is reaches 1.1 volt after 4 seconds and finally reaches a steady state value of 2 volts. Then what should be the system time constant? This is the question. What should be the system time constant? But while looking this, he is saying that first order response, first order system, a first order system. So no doubt, this is the first order system. Now you have to be identify step response or unit step response. Now see, the level is constant and which is not 1, some k. Therefore, this is first order step response. Like that, you have to have a conclusion first. This is the first order step response. What is the first order step response? Just now you are identifying the response is nothing but k into 1 minus e power minus t by tau. So the response is reaches 1.1 volt after 4 seconds and finally reaches a steady state value of, what is the steady state value? The steady state value of 2 volts, and only one unknown parameter here, system time constant tau, he want to calculate it. He is asking, what is system time constant tau? This is the only unknown parameter. The response reaches 1.1 volt after 4 seconds, finally reaches a steady state value of 2 volts. What is the system time constant? Simplify this and you can get the system time constant. I think this is some 5.0 something, 5 seconds, approximately 5 seconds. I think, just check it. Okay. Voltage cancel, 1.1 by 2 equal to 1 minus, then apply the anti-logarithm, you can get. Okay. This is the way you can find what is the first order step response or unit step response. First you want to confirm and use that formula or this formula. Okay. Only the difference is k equal to 1 for unit step. Note down this. Now question number 4 is also similar. Okay, you can easily solve that one, but anyway we'll see. Question number 4 is as it is same as question number 3. Question number 4. Now a thermometer represents a first order system. A thermometer represents a first order system. Is initially at rest position. The response will take 1 minute. The response will take 1 minute, means 60 seconds. To reach what? The response will take 1 minute. A thermometer represents a first order system. The response will take 1 minute to indicate 98% of the unit step. In the question is mentioned 98% of the unit step, means very simple. A unit step means the steady state value is 1. Then the first order in the question itself given. This is the first order which response, step or unit step. Now this is a unit step, therefore first order unit step response. The response will reach 98%. The response will reach 98%. The response will reach 98%. And it will take a time of 60 seconds. And finally the response reaches steady state value of 1. And what should be the system time constant? What should be the system time constant? Okay. What should be? This here is also same question. And what is the system time constant? Now this is 12.36 seconds. You just check this one also. Okay. This is the system time constant. But now the question itself is mentioning first order system, no doubt. But it is a unit step response or step response, you have to be identified. Now the steady state level is 1. This is a unit step response. Previously steady state value is 2. Therefore this is a step response. Take this one. Now, question number 5 in workbook, question number 5. Now see here, in these two cases, what is the rest position? Ki equal to 0 and Kf equal to K here. Kf is equal to 1 here. Ki equal to 0. Because these two are the first order step response and unit step response starts at rest position. So this is Kf equal to K or Kf equal to 1 here. Am I right or not? The Kf equal to K or Kf equal to 1 for unit step input. But now see the question number 5. The question number 5 is given. Again a thermometer. Again a first order system is mentioned. But in the question he is mentioned that a thermometer represents a first order system is subjected to a thermometer represents a first order system is subjected to a sudden temperature changes. A thermometer represents a first order system is subjected to a sudden temperature changes from 25 degrees centigrade to 150 degrees centigrade. He is giving this. A thermometer represents a first order system is subjected to 25 degrees centigrade to 150 degrees centigrade. First of all, no confusion, first order system, because in the question itself he is mentioned a thermometer represents a first order system. Now we have a identification that unit step response or step response. What is the reference level? The reference level is 150. Therefore, no doubt this is the first order step response. But the problem with this question and the previous question is, in the previous questions, the initial values is 0. The initial value is Ki equal to 0, the Ki equal to 0. But here the initial value is not 0. It is starts at rest. It is starts at some level and go to some other level. Therefore, this is the response of the first order, not start at the rest position. Therefore, then that step response is represented as final value plus initial value minus final value into e power minus t by tau. Same one time constant first order. So if Ki equal to 0, see here, if you have any doubt, Ki equal to 0, therefore Kf plus 0 minus Kf into e power minus t by tau. Therefore again same, Kf if you take it as common, 1 minus e power minus t by tau. The same answer you are getting here. Same answer. Kf equal to K or Kf equal to 1 here. Okay. Same answer. Okay. Therefore, this is the first order step response. If the response is not start at the rest position, then what is asking? A thermometer represents a first order system is subject to a temperature. Initially is 25 degrees centigrade. Finally is 150 degrees centigrade. Now finally is 150 degrees centigrade, and he is having a system time constant of 5 seconds. Is having a system time constant of 5 seconds. What is the question he is asking? What temperature will be indicated by thermometer after 10 seconds? Means what is the response? After 10 seconds, what is the response? Simplify this. This is 133 degrees centigrade is the response. Note on the student, this one.